Hello, Andy Jacobs here from Arizona State University. I'm going to tell you today a little bit about the HERA telescope and what it looks like and what it's designed to do, and some of the details about our data analysis. But mostly, a lot of that will be left to future talks. So I'll give you an overview and then we'll break it down from there. So HERA is a large collaboration with about 100 and so people scattered around the world, with many institutions in the United States and Europe, and collaborators in South Africa. There are a number of supporting partners, the main ones being the National Science Foundation in the United States and the Gordon and Betty Moore Foundation, as well as many of the institution partners as well. A lot of people working really hard. As you'll probably already have heard, the big picture scientifically is to measure the 21 centimeter line from neutral hydrogen. And this is something that is available throughout the cosmic timeline, and there's lots of different science cases for looking at different epochs. And so the context that we're building this array in is one where we're going after a very specific range of redshifts where we can do specific kinds of astrophysics and cosmology, but there is a wider range, and there's the vigorous community of instrument builders and theorists going after a lot of different interesting things in different epochs. HERA specifically is really targeting this time period during the onset of the first stars and into reionization, so the last gasp of neutral gas in the universe when stars turned on. And it observationally sits at an interesting point between the cosmic microwave background and large optical and infrared observatories. So we can look for overlaps cosmologically between things like the CMB probes and astrophysically things like JWST. Specifically, we're zooming in a little bit. You probably have seen a light cone like this already. This is a map 2D simulation showing a slice through the universe of hydrogen and what it might look like. It's in absorption, it's blue, and when it's in emission, it's red. And you can see that there's quite a lot going on. They're different depending on what epoch you look at. And HERA specifically is targeting the end of the time, this time period from redshifts about 14 to 6, and specifically looking at the fluctuations. So on the top there, you can see this slice in 2 dimensions, and then at the bottom is the globally average signal where there is additional information to be found. Later, we'll be, in fact, currently upgrading HERA to phase 2, which will add a significant redshift extension to target that deep trough there, that blue area, where we think that there's further interesting things to go after. Specifically, what we're measuring is the power spectrum. So the power spectrum is a probe of variation as a function of size scale, basically. What you're seeing here is a simulation showing the birth of ionized bubbles on the left and a power spectrum on the right, where K modes that are small, on the x-axis, 0.1 K modes is about 10 megaparsecs in size, and then all the way up to 1. So you've got the largest things on the left, and you can see as the ionized bubbles really get big, that small K power grows, and then the whole thing drops away. And so this is a fully 3D probe. We're measuring the 3D universe at different slices in redshift, but we can look at it as it evolves too. So we get this power spectrum as a function of K and redshift. That's the thing we're trying to measure. And this is what we can compare against models to infer the physics going on underneath. Specifically, what HERA is going after is, like I said before, these redshift ranges that are roughly between 6 to 14, and then maybe hopefully extending out to as high as 20. And if you look at the sensitivity that we're attempting to put on the sky, it's this line here is a function of redshift. So pick a mode from that plot that I showed you before, power spectrum evolving as a function redshift. Pick a single K mode and look at it as a function of redshift, and you get this plot here. And you can see that depending on the models, we've got a couple, the orange and the red. You can see that there's quite a large difference depending on what's going on in the early universe. So the kinds of sensitivities we're hoping to put on these models is in the range of 30 sigma and higher, depending on the model, which is mostly due to the large collecting area that we're adding to the picture, which I'll tell you about in a second. So this is one way of looking at it. Another way of looking at it is just the various power spectra that people have measured. So how have we been doing? This is the context that we're in right now, without any deep HERA measurements on here yet. So these are different power spectrum limits. These are measures, upper limits on the power. The power can't be any higher than this according to these measurements. And there's a bunch of them here from various telescopes like the NWA and GMRT and the Paper Telescope, which is a precursor to HERA, and LOFAR. And you can see that there's a general trend where rising noise as you go to smaller scales means that power spectra are generally tilted up with K. And that there's also different modes where there's more sensitivity, and that has to do with the spectrum sampling function, which we can talk about more in detail later. So HERA is aiming to put lower limits than this on the board, and you can see we're all right around 10 to the 4, a little bit, a few times 10 to the 3 in these units. So HERA itself is a targeted experiment, which means that it's really aimed at just this specific science question. We're not aiming to do other science at lower frequencies, although accidents do happen. This is what it looks like. What it looked like a little while ago, anyway. This is it's a collection of 14-meter dishes, all packed really tightly together. You can see them there, sort of going off into the distance, and each one has a feed at the center, which is hung from 3 poles, just like Arecibo was. The dish itself is made of low-cost materials. It's made out of PVC and wood and things like that. The mesh itself is laying there. When it presses down on that PVC, it hangs nicely in a parabola-like shape, and focused on that feed at the top. The net size of it is such that it adds up to being about a fifth of 0.05 square kilometers. So a hefty amount. You can almost start using that unit, and it's being built in South Africa, like I said before. So you can see there it's in the desert. The UV configuration, the number of size scales that we measure, this is a typical metric that radio interferometers use to estimate how good of sky reconstruction they can do, is very good because it's very dense. The dishes are all right next to each other, and that means we sample all of the scales, ranging from the scale between 2 dishes out to the largest array. Basically it's a fully sampled aperture. It isn't a perfect situation, though, because there are gaps between the dishes, and that is one of its limitations. One of the other things that we've done is made the array redundant, where each of those, because it's a grid shape, because they're all packed together right next to each other, you get the same baseline many times, and that lets us do things like calibration and average together those baselines before we do anything else, which improves our signal to noise. The kind of coverage that this gives us is what brings the sensitivity. So just roughly speaking, this kind of sensitivity gives you constraints that look kind of like this. So this is a typical set of power spectra that you might imagine some model predictions, and these are our really rough early sensitivity projections for those, and nothing has really changed to really alter this picture too terribly much. We're expecting to be able to constrain lots of different models, depending mainly on our ability to constrain and remove foregrounds. So we've divided the project up into 2 phases. The first phase used a lot of the hardware left over from the paper experiment, specifically those feeds, which were taken out of the paper dishes, which you can see there in the background, and put hanging over the dishes. And we used the existing front end system and the digitizers to build a first draft array, if you will, using about 70 antennas. The main limitation being just the existing cables didn't allow us to do more antennas than that, even though we had more, we did have more feeds. These are some of the technical details if you're interested. It ended up being a coverage, frequency coverage of about 100 to 200 megahertz, which corresponds to a redshift range of 13 to 5.5, which covers the full likely range that reionization is likely to take place in. And it was used to observe and to test new upgraded hardware, and in the first couple of years of the project. More recently, we moved on to a phase 2. Phase 2 adds a different broadband antenna, totally new feed. You can see there those shiny big feeds hanging there. Those are now sensitive all the way down to 50 megahertz, which gives us coverage out to 20 something in redshift, depending on where exactly you draw the line. It also adds quite a few more channels, which lets us do a better job rejecting interference and things like that. We've completely replaced the correlator and the analog front end. Basically, the only thing that's the same are the dishes. Here's a comparison. So the left is the phase 1, which has that narrower band dipole structure hanging up there, and then on the right is the Vivaldi, just for comparison. We've been building out since about 2015, when so there's a picture of the South Africa site from orbit. There on the right is the Meerkat telescope, and there on the left is HERA down there. It's on a circle. It's been carved out for us, and the build out started in 2016 with a small array of 19 dishes. In 2017, we added 60 new dishes, still using those old feeds. In 2018, we began testing the HERA system upgrade, the phase 2 upgrade with the new RF stuff. And in 2019, we added a bunch of new dishes. And then soon after that, COVID hit. But we were able to continue building, and the array is now complete. The only thing left are a few outriggers that we plan to add later. So as we did this, we also observed. So here's a rough timeline. Every year would turn on the array when the sky was right, and observe with whatever dishes we had. And as we added more dishes, things got better. What you're seeing there is a drift scan from our real first season of data, which was observed in 2017. So the sky is just scanning past. HERA sits there looking straight up, turning as the Earth turns. And you can see the sources, mostly extragalactic sources moving on overhead. So we collected a good chunk of data, a few hundred nights, and have been, especially through the COVID years when access to site is limited, really digging into that and building up our analysis capabilities, which is mostly what you're going to hear about today from Josh Dillon and Nick Kern, to come after, and then later, which all of that analysis led to a data release and a set of result papers, which have been used to provide an initial scientific interpretation, which Andre Messenger will talk about. So I'll just give a really quick top-level overview of that stuff, and then let them handle the details. One of the things that we really targeted with this array upgrade was the reduction of systematics. So just to give you a kind of a view into this, on the left is a power spectrum. This is in P of K units. So to get the delta squared units, you have to multiply by K cubed, and everything tilts up. These are much more useful units to use for looking at data. And you can see that there's a central peak, and that's where we expect foregrounds, which are smooth spectrum, to live. And outside of that, there's bumps, and those bumps turn out to be related to systematics, reflections, and cross-coupling within our cable system. And you can see here that an example of application of a a filtering scheme that that removes these. Nick will talk more about this in his time. That's one of the things that's been accomplished. The second one is really understanding how to calibrate an array like this. But a redundant array, you can use the fact that you are measuring the same baseline many times. So that gives you an additional way to calibrate your. It doesn't actually it doesn't solve all your problems, and in fact, redundancy in some cases adds them. And Josh Dillon will talk about this more later. But it really lets you see what's going on when you have a limited number of antennas. So given some of those tools, we were able to produce an internal data set, which we then took to a power spectrum. When you do that, you have to pick which data you're going to use. The main two questions are which frequencies, meaning which redshifts, and which parts of the sky. So we did a careful down select on the basis of what we knew about the flagging going on and that sort of thing. Nick will tell us a little bit more about that. But on the right there, you can see a map of the sky and the stripe that HERA makes as it draws across. And we picked out a couple of local sidereal times that mapped to quiet chunks of the sky. The idea being the signal is cosmological. You can look for it in any direction. It should be the same roughly in any direction. And so we pick a few, and then they ought to be the same. We recorded data with this smaller array, like I said before, and Nick will tell us about that. And then we did some calibration tricks where we, for example, tried to emphasize the spectral smoothness of the solutions, and Josh will tell us about that. One thing that they might not tell us about because we don't have time is the fact that one of the things that we did when we were reducing, trying to pick which parts of the sky we were going to look at, is we noticed that one really specific part of the sky had a very odd it made a bump in the power spectrum in an odd place, and it turns out, and maybe we can talk about this later, that it was only in the polarization part of the analysis, and that meant that it was almost certainly, and it was a pulsar. So we saw an object, which is pretty cool. So this all led to a set of power spectra in different redshift bins and sky locations, which look like this, and you can see that most of them are generally error bars that go through 0, which suggests that they are not in fact seeing anything. So we interpreted this as an upper limit. Not all of them are. This is why having multiple skies that are independent is useful. Nick will explain how we interpreted this. This leads to a limit. So this is the similar plot like I showed you before. You have different power spectrum limits. And then on the bottom, you can now see some example models where we're trying to get to, and the new result from HERA is the pink triangles there. So those are pretty low, and we're hoping to do still better in the future with a lot more data that we have in the can. As a point of comparison, you can see here what the power spectrum looks like. So now we have redshift as color, and these are all the data points, not just one. And you can see that some of the bins are lower than others. One thing I do want to mention is the HERA site, which is in South Africa, like I said before. They have, like everyone else, been impacted by COVID, and they continue to do amazing work on site. You can see that they've got they've fared. If you look at the case rates, they've fared pretty well. If you look though at the death rate, it's a different story, and they've had a hard time of it, about as bad as any of us. And at times when everyone else was or most everyone else was doing okay. So they've continued to do really great work on site, building through this whole thing. Without any of us being able to go there for over 18 months, we were unable to go to site, push a button, fix anything, and it's a real testament to their stick-to-itiveness and resourcefulness that we were able to get all the dishes built and get all of the feeds assembled and get everything and do a lot of amazing remote debugging work. We've really learned how to do things remotely. not just Zoom recordings. So all this data that we'll be talking about for the rest of today is available online on our website there, reionization.org. The data release includes all the power spectra and there's also a memo series with detailed notes about the data reduction and a lot of the work that went into the background. I should also say that there are a number of supporting papers which give even more detail about our analysis process, validation process, and some of the other things that have gone into an error bar calculation, that sort of thing. So I will be on later to see you all during the question period once I have woken up. Thank you for your time.